Organic Chemistry, Chem 212, Exam 1 Material, Part 3. Alkanes and cycloalkanes. To start off, let's get an idea of some of the functional groups we'll need to know right off the bat here. You need to memorize the name and the general structure for the different functional groups. Functional groups are groups of atoms within a molecule that have a characteristic chemical behavior. The chemistry of organic molecules is determined from the functional group. There are three categories of functional groups. We have carbon-carbon, single bonds, and multiple bonds. We have a carbon atom bonded to an electronegative atom. And we have the carbonyl groups where we have carbon double bonded to oxygen. When we take a look at these functional groups, if you look at the bottom of the slide, it says R is a generalization for any group. Typically, it's a carbon group, but it actually can be anything. So pretty much in what we're looking at here, it can be carbon, it could be carbon groups, it could be anything. In fact, sometimes people, when they see the letter R, they'll say that's the rest of the molecule. If you take a look at carbon-carbon multiple bonds, if you look at our first one here, alkene, I have a carbon-carbon double bond. And on my R groups, if you notice, one of them doesn't have any kind of a tick mark. This one has 1, 2, and 3. Sometimes when you do R groups, you'll put tick marks on them so you can differentiate from them, for example, in a reaction on where did they start from and where are they going. There's other reasons why you would use them, and sometimes you don't use them at all. So I wanted to give you an example of what you could do if you wanted to label them. One other thing about R groups, even with the tick marks, they could be the same as each other or different. So for example, this R group could be a methyl, and this one could also be a methyl, and this one could be different. It just depends. Remember, it means rest of the molecule. The functional group of an alkene, the key feature is the carbon-carbon double bond, and what else is coming off of it depends on which alkene we're talking about. The ene ending means we have a double bond. An alkyne, here we have a yne ending, and the Y part here tells me I have a triple bond. So again, we have the feature, the main feature of the functional group alkyne would be the carbon-carbon triple bond. And because carbon can only have 4 bonds total, we only have one R group for each of these carbons. Again, these R groups can be the same as each other or different. The arene group, typically that's a benzene ring, and we can have other things coming off the benzene ring. There's a couple of ways we can represent benzene. We can see here we have alternating double bonds, or you can show the aromaticity by having the circle in there, either one. So why don't we go ahead and put or on here, because you could show either of these if you were asked to draw these structures. The second type is when we have carbon to an electronegative atom. We have an alkyl halide, so our group would be some sort of carbon group. So for example, one of the smallest ones we could have would be CH3, and let's make a halide Br this time. Typically with organic chemistry, X represents a halogen, and the word halide means I have a halogen, and I could have picked any of the 4 halogens there. And an R group can be any size carbon, so this is an example of an alkyl halide. The alcohol group, the key feature of that is this OH group here. The smallest of the alcohols would be methyl alcohol, where the R group is a methyl group, and we have an OH, so that would be classified as an alcohol. So look for the OH group to classify it as an alcohol. An ether group is when you have an oxygen with a carbon on each side of it. So the smallest ether we have, let's go ahead and put a methyl group there. We have an oxygen, and I'm going to go ahead and make it a symmetrical ether. Both R groups are the same. So this is the general structure for an ether. Here's an example here. So the feature of an ether is we have oxygen with a carbon on each side of it. And amine is when we have nitrogen and we have 3 R groups. So here's something that's interesting about the R groups. Remember I said it can be a carbon or a hydrogen? Well, if we have what's called a primary amine, that means I have nitrogen with 2 hydrogens and 1 R group. If I have what's called a secondary amine, I have nitrogen with 1 hydrogen and, oops, let me get my R better, 2 R groups. If I have what's called a tertiary amine, I have nitrogen with no hydrogens and how many R groups? 3. So this is a case where nitrogen has to have at least one carbon. This R group here has to be a carbon. If this were also a hydrogen, it would be ammonia, and that's not an organic compound. So in this case, you have to have at least one carbon group to call it amine. You cannot say NH3, this is not an amine. You can't have all R groups hydrogen in this case. A thiol is actually the sulfur analog of an alcohol, and so its functional group is SH. And you can see here, I'm going to go ahead and just use the methyl group because it's a nice small group to draw. And here would be an example. Notice the only difference between an alcohol and a thiol is I have an oxygen here and I have a sulfur here. And a sulfide, it's the analog of ether. And in this case, instead of having oxygen in the middle, I have a sulfide. Here we have the third type, carbon double bonded to oxygen. These are all carbonyl compounds. Now, this is only 6 of them. There's going to be a lot more as we go through the next 2 semesters of this course. So we're going to start off by having you learn aldehyde. In an aldehyde, now notice, well, before I get to aldehyde, notice every one of these has a C double bond O group. Are you seeing that for every one of those? So that's what makes these in the same function, in the same grouping here. Now, the specific functional group aldehyde, the key feature is it has a hydrogen directly attached to this carbonyl. That's what makes it an aldehyde. This R group over here may be hydrogen, or it can be a carbon. So R can be a hydrogen in this case. In fact, that would be the smallest of the aldehydes, known as formaldehyde. But it can also be a big carbon group or a small carbon group. Now, how a ketone differs from an aldehyde is these R's right here cannot be hydrogen. So you might want to put R cannot be hydrogen. Because take a look at my ketone one more time, if this were a hydrogen, it would revert back to the aldehyde family. Or if this were a hydrogen, it would revert back to the aldehyde family. So in this case, R cannot be a hydrogen. It's going to be some sort of a carbon group. Carboxylic acid, take a look here. I have an OH here, where the aldehyde had just an H. This has an OH. And this R can be hydrogen. Ester has an OR group here. So in this case, this R prime, the one I have is the tick mark, this cannot be, is not equal to, but I know it's kind of off a little, cannot be a hydrogen. If this were a hydrogen, it would revert back to the carboxylic acid group. This R can be a hydrogen. All right, we have an amide. Amide, this is different than an amine. Do you notice there's a D right here? An amide is when you have a carbonyl group, and right next door to it is a nitrogen. And in this case, all R's can be hydrogen. Acid halide. So we just looked earlier, we saw the word halide, and I told you that typically X represents halogens. So this could be any of the halogens here. R can be a hydrogen. And when we have halides, this is called an acid halide, this structure here. But what would it look like if I had an acid chloride instead? An acid chloride would be exactly the same structure. It would have an R group, my carbonyl group. But instead of showing an X there, you would put a Cl instead. So when you learn acid halide, you're actually learning 4 functional groups. Well, actually 5. Acid halide is generic with an X. Acid chloride would be a Cl there. Acid bromide, yep, that would have a Br. And we also have our other 2 halogens, iodine and fluoride. So make sure you know that any of the halogens could be there. This is another one of those posters from Compound Interest. Their website again is www.compoundchem.com. You can see it on the bottom here too. And I liked how they took these functional groups in organic chemistry and kind of put them together in different groups, and they colorized them and all kind of stuff like that. So this is kind of a nice little poster for you to take a look at and help you learn some of the functional groups. On this slide, what I want you to do is to identify the functional groups in this compound. And what you want to do is you probably should circle them and write their name next to it. I want you to go ahead and you can go back to your list on the different functional group I have in your other slides and find the different functional groups. Pause the video, work on this, come back and check your work. Okay, you may not have them in the same order as me. I found 5 of them. Arene, that would be this one right here. That would be the aromatic, so that's the arene. I also found a carboxylic acid. The carboxylic acid, it's kind of upside down right here, but this is my carboxylic acid. I also found an alkene. I want you to take a look again and see if you can find the alkene if you didn't find it. Alkene is right here. It's actually going vertical. That's the alkene. It's a carbon-carbon double bond. And amine, right here, this is my amine. It goes down to the R group, pretty complicated R group. And ether is this group right here. We have an R group here that happens to be a methyl group, and the R group on the other side is big and complicated, but it's still considered an ether. How'd you do? So we're going to go ahead and take a look at alkanes and then also alkane isomers. So let's start off with alkane. Alkanes are compounds with a carbon-carbon single bond, and we also have a carbon-hydrogen bond. There are no other functional groups there, so no oxygen, sulfurs, or nitrogens, or double or triple bonds, nothing like that. Just plain old hydrocarbons. In fact, a lot of times they just call these hydrocarbons. So let's take a look at some expanded structural formulas of the smallest of the alkane family. Methane is the smallest here. Carbon has 4 bonds, 4 hydrogens. Ethane, 2 carbons, the most number of hydrogens that would allow me to have the 2 carbons completely filled with the maximum number of hydrogens would be 6. Propane, when I have 3 carbons, notice again the maximum number of hydrogens I can have in this case would be 8. And butane, when I have 4 carbons, the maximum number of hydrogens to fill this up completely, that would be 10. When we look at the ending of all of these, and I know methane technically doesn't have any kind of carbon-carbon bond, but the ane ending is telling me single bond. Let's go ahead and take a look at all the alkanes. This is ethane, carbon-carbon, single bond. This ane ending is telling me carbon-carbon. Do you see all the single bonds? And the same thing with butane. So the ending of our alkane gives us the ane ending, and that tells us in the name the bonding that happens. That's something that I really like about the nomenclature of organic chemistry. The name tells us the structure. Well, the new piece that's in here that we haven't quite gotten to yet is the prefix before the ane. Meth means 1 carbon, eth means 2 carbons, prop means 3 carbons, and but means 4 carbons. And you might have seen this in some of the other things we've already looked at so far this semester. We have meth, eth, prop, and but representing 1, 2, 3, and 4 carbons. That's something you're going to want to memorize towards the beginning. In fact, I think a few slides from now I also have it for you. Well, one of the things I also pointed out as I was describing these structures is you notice that the maximum number of bonds carbon can have is 4. In fact, it prefers 4. So the maximum number of hydrogens in this case would be 4. I'd have 1 carbon and 4 hydrogens. When I had 2 carbons, the maximum to completely fill this up with hydrogens was 6, and so on. Well, they figured out, or actually we can even see it, that there's a formula for the alkane. If it has no rings, so it can't be a cycloalkane, the formula of this would, and the ratio to carbons to hydrogens when you have an alkane is CnH2n plus 2, where C, or actually N, is the number of carbons. So let's take a look at this. Look at this formula, CnH2n plus 2. How many carbons do I have in methane? 1. So if I put the number 1 here, 2 times 1 is 2 plus 2 is 4. That means this methane, to be an alkane, would have to have 1 carbon and 4 hydrogens. Let's apply that all the way down here to butane. We have 1, 2, 3, 4 carbons. So if C is 4, then that would be N is 4. 2 times 4 is 8, plus 2 is 10. Did you notice we only had 10 here? So not only is CnH2n plus 2 the formula when we have an alkane, that's also when we have a saturated molecule. So let's take a look at some isomers before we get to naming these compounds. Your model kit, go ahead and get your model kit out. You need to build these models so they make more sense. I know I have the models here on paper, but it makes a lot more sense when you can build them, when you can move them around, turn them around, 3D, all that kind of good stuff. So go ahead and pause the video, get out 4 carbons, 10 hydrogens, and go ahead and build this first butane here, 4 carbons in a row, filling in all the hydrogens. So go ahead and pause the video and then come on back and I will talk to you more about isomers. Okay, so hopefully you have the model together. If not, pause the video, go ahead and make it. All right, alkane isomers. Isomers have the same molecular formula, but a different structural formula. Both of these molecules here have the molecular formula C4H10. This is a molecular formula right here. Now, the structure of this one is a straight chain, whereas this one has 3 carbons in a row, but it has a branch of 1 methyl group coming off of it here, off of carbon number 2. They are not the same as each other. They do have in common their molecular formula, but they have different properties and they have different names. They are different compounds from each other. So what we do with this is, if you're given a molecular formula, you need to be able to find all the isomers that go with it. In this case, C4, which is butane, has 2 different structures. So if you were to answer the question, if the question was asked C4H10, how many isomers are there? When asked how many isomers, how many structures do they have? In this case, there will be 2. So isomers pretty much happen after we have 4 carbons or more. So this is one of our first hydrocarbon isomers. Here's a slide showing 5 carbons, pentane. Notice I have 3 structures, so that means I have 3 isomers. So we have pentane, which is a straight chain. Oh, and I mentioned straight chain on the last slide, and you might be thinking it's straight on paper, but when you build the molecule, remember I want you to build these molecules and also build the isomer next to it. You're going to see that it zigzags like this. So even though it zigzags, we still call it a straight chain because the longest continuous chain of carbon is right there. There's 5 in a row. Do you guys see that? So this is still called a straight chain, understanding that it zigzags. So when you need to figure out isomers, right now I'm giving you how many isomers there are, but let's say you were given a molecular formula and the question was, how many isomers are there? Well, one way to do this is to do this very systematically. So do you see how I have 5 carbons here? What I would do is I would go ahead and write down 5 carbons in a row, because I know the first one that I can come up with most simply is just a straight chain of 1, 2, 3, 4, 5. Now I'm actually going to come back and fill in the hydrogens later. I'm doing the backbone carbon skeleton structure, and I will come back and fill in the hydrogens. But the reason why I don't want to do them right away is because once I start putting the hydrogens in, it gets a little sloppier, it gets a little more complicated, and it's harder to see the backbone carbon structure. So what I'm going to do next is, instead of putting 5 in a row, I'm going to put 4 in a row. And I'm going to go ahead and now I'm going to branch a carbon off of this. Well, I would like you to go ahead and build the model of pentane, 5 carbons in a row, throw in all the hydrogens if you want, or you can just do the backbone structure. But I want you to remove 1 carbon. And then I want you to take that branch. It's going to come off of one of these carbons. I want you with your model kit to go ahead and put it on the end carbon for me. And you're going to notice when you put it on the end carbon, you actually made this one again. Whenever you're doing branching, you can never branch off an end carbon because you've actually, in this case, made the one we did before. If I were to look at this and say, okay, my longest continuous chain of carbons, regardless if it bends and twists, is 5. Well, in this case, the longest continuous chain of carbons, regardless if it bends and twists, is also 5. I just happen to bend it a little bit. This is still a straight chain of 5, and this is a straight chain of 5. Okay, I'm going to go ahead and clear the slide, and I'm going to get rid of those circles, and I'm going to continue. So I went ahead and just rewrote this. It's a little, I had to erase it, so I'm going to start over. So remember, when you're trying to figure out how many isomers you have, you never put isomers off an end. That means you're repeating that one you had before. So you can go 1 carbon in and do that. So now I have a methyl group, a single carbon coming off carbon number 2 of the main chain. Take a look at this one up here. Do you see how I have 4 carbons in a row? And this is coming off carbon number 2? Well, the one up here is the same as mine down here. The only difference is they're viewing it from right to left, and on mine, I'm viewing it from left to right. It's the same molecule. When we start talking about the branches, we go from either the left side or the right side, and we always give it the lowest possible number. Let's even look at this model version here. Do you see this branch coming off? It's closer to this end, so this would be carbon number 1 of my parent chain. This would be 2, this would be 3, and this would be 4. And this is where we get 1, 2, 3, 4, the last name, butane. Again, we're going to do naming a little bit later, but I want you to start seeing some of this. Do you see bute? Meaning 4, ANE, single bond. So the parent, the longest continuous chain, regardless if it bends and twists, is butane. That's its last name. And then coming off of this is a single methyl group right here. Do you see this methyl group? It's coming off carbon number 2. That's where 2-methyl butane comes from. All right, so that's kind of detouring just a minute on the numbering system and the branching system. So if I want to figure out what other isomers I have, if I were to draw 4 of these in a row again, I'll just put it down here, and I were to go ahead, I already know I can't branch off an N carbon. I already branched off of this one. What if I were to branch off of this one? Would that be any different than one before it? Well, actually, it's the same as this one. The only thing is, it's actually like the one up here, is I have a methyl group coming off carbon number 2. And it doesn't matter if I draw my methyl group going down or up. It's still on carbon number 2. So this is not another isomer. It's actually the same as that. So I would not want to do that. So here's another hint or tip. You cannot branch off an N carbon. And once you get symmetrically to the middle of it, you're done because you start repeating. Now we also have something else that can happen. I have 3 carbons in a row, and no one ever said you couldn't branch 2 carbons. Remember, I have 5 total to show. So I'm not going to branch off an N. We already established we can't do that. But nobody said I couldn't do 2 of them coming off of here. And that's what happened here. Do you see I have a carbon here on the left and the right? That makes a 3 main chain with 1 above and 1 below. So taking a look at this, my parent chain is 3 carbons. The prefix for 3 is prop. They're all single bonded. You guys see that? The ane ending. And I have not 1, but 2 methyl groups coming off of that. Do you see the di in front of methyl? That's where we use those. I have 2 methyl groups. And the numbers in front of here tell me where they live on the parent chain. And even if they're the same thing, in this case they're both methyl, and even if they live on the same carbon, everybody gets their own individual address. So the name of this compound would be 2,2-dimethylpropane. All right, so again, kind of combining the naming with the isomers. So we have 3 isomers, we have 3 structures. I'm going to go ahead and clean this up again, and I'm going to show you how to put in your hydrogens. All right, I went ahead and got all that stuff off of there because I want to now show you how to know how many hydrogens to put on there. So that first thing that we did was to figure out how many isomers we have. I kind of threw in a little bit of the naming to help you understand some of the notation we have. And now we need to go through and take a look at how many hydrogens do we need to complete our 4 bonds for carbon. So what we're going to do for just a minute here is I'm going to ask you, how many bonds does this carbon have right now, the way it's drawn in its skeletal form? Well, the answer is it has 1 bond. How many bonds does this carbon have right now, the way it's drawn? It would have 2 bonds, 1 to a carbon on the left and 1 to the right. And this one, 2 left and right, again 2, and then this one only has 1. When we get to this one here, how many bonds to carbon does this guy have right now? 1. This one, how many bonds to carbon does it have? 3. 1, 2, 3. Don't forget to look down. This one has 2 and this one has 1. And then this shape, this has how many bonds to carbon? 1. In fact, all 4 of these around there all have 1. But look at the guy in the middle. How many bonds to carbon does he have? He actually has 4. So the reason why I wanted to go through that is sometimes we have to look at the carbon and determine how many other carbons it's bonded to. So I wanted to give you that chance to take a really good look at that. So we're going to take advantage of talking about how many bonds it already has to carbon to figure out how many hydrogens we need to add to it. Now I know you have the answer up here, but let's look down here. If this carbon has one bond to carbon, how many hydrogens does it need to fulfill its 4-bond total? Well, the answer is 3. Okay, and I'll write that in just a minute. This has 2 bonds to carbon, so how many hydrogens does it need to get 4 bonds total? The answer is 2. And you can see this has 2 bonds to carbon. How many hydrogens? 2. This one has 2 bonds to carbon. How many hydrogens? 2. And this one has 1 bond to carbon. How many hydrogens? 3. All right, let me show you a little trick that I do. We know this guy here needs how many carbons again? 3. Take a look at this. I use that bond line to make an H because you don't have to show horizontal single bonds. We're allowed to draw the symbols next to each other without a bond line. Now you always have to show verticals, but not that one. So take a look at this. Now this has how many bonds to carbon? You can see once I put in the hydrogens it kind of starts getting messy, so that's why we talked about it first. This has 1 bond to carbon, 2 bonds to carbon, so it needs 2 hydrogens. This guy needed 2, this guy needed 2, and this guy needed 3. There's my condensed structural formula for pentane. Let's do our condensed structural formula for 2-methylbutane. This carbon needs how many hydrogens? 3. This carbon needs how many hydrogens? Okay, it has a bond to carbon, 1, 2, 3 bonds to carbon, so it only needs 1 hydrogen. This guy has 1 bond, so it needs 3 hydrogens. This guy needs 2, and this one needs how many? 3. Do you see how we have a space between these two? Let's say you're writing these and you get a space that just seems a little bit too big. You can also put in a bond line. A horizontal bond line is optional, but you can also put it in if it looks like things are written too far away from each other to help for clarification. Don't forget I know it's not so neat here, me using this digital pen here, but don't forget the numbers on these hydrogens all have to be subscripted. All right, this carbon right here, how many bonds does he have to carbon right now? 1. So how many hydrogens does he need? 3. In fact, you'll see that every one of these, they're identical to each other. They're all CH3 groups. So one of the things you can do on the left-hand side, notice that I put CH3 on all of these, but one of the things you can do on the left-hand side is this group right here on the left-hand side, you're allowed to put the H's on the left-hand side. Your textbook does that a lot. So only on the left-hand side. All the other guys, the hydrogens have to be to the right. Notice these are on the right. Only on the very last one can you put the hydrogens on the left. All right, this carbon in the middle, does it need any hydrogens? Well, no, because it already has 1, 2, 3, 4 bonds. One of the things that I check when you take your exam, one of the things that I check is I go through and I count how many bonds to carbon you have and how many bonds hydrogen has. I go through and check that. So make sure you take the time on the exam to go back and make sure carbon has 4 bonds. If it doesn't have enough bonds, are you missing hydrogens or what else are you missing? All right, so I went ahead and cleaned up all my notes there. Let's take a look. Alkanes with carbons connected to no more than 2 other carbons are known as straight chain or normal alkanes. So that would be this example here. This is called a normal or straight chain. Alkanes with 1 or more carbons connected to 2 or 3 carbons are called branches. So this 2-methylbutane has 1 branch, and 2,2-dimethylpropane has 2 branches. All right, so we looked at 4 carbons and 5 carbons and how many isomers there are. If you have 6 carbons and it's an alkane, you have 5 isomers. I highly recommend taking out a piece of paper and finding the 5 isomers. Now, I don't have the answers for you. That's something you get to look up on your own, or you get to practice on your own. C7H16 has 9 isomers. It's possible that I might ask you to draw probably, 10 or less isomers, so I would highly recommend going ahead and practicing the C7, the total of 9 isomers, but after that I would never ask you to draw 18 or 35 isomers on an exam. What I want you to get from this is if you have this, take a look at this. Look at how quickly the number of isomers increase. In fact, it's n factorial. And the number of carbons, n factorial, is how we get how many isomers. So just with 10 carbons, we have 75 isomers. Now remember, this is just carbons and hydrogens. We're not bringing in sulfur, nitrogen, oxygen, nothing like that. It's just 75 different isomers. And this also does not include double bonds or triple bonds or rings. This is just plain old hydrocarbons. And take a look at here. As soon as we get 30 carbons, we're up to the billions right here. And this number, I don't even know what that number is. That's pretty amazing. And that's only 40 carbons. You do not have to memorize this page at all. Do not memorize that 9 carbons has 35 isomers. This is just for you to get an idea of the vast amount of organic compounds that are out there. And these are the simplest ones. Constitutional isomers. These are isomers that differ in how their atoms are arranged in chains. So that's really what we've been looking at already with the alkanes. We've been looking at constitutional isomers. So this is expanding the definition of an isomer a little bit more. We can have constitutional isomers with atoms other than carbon. So here's a few examples. We can have, and this would be the example we had earlier, different carbon skeletons where we have 3 carbons as our parent chain with a methyl group coming off of carbon 2, and that's a C4H10. And we also had butane as a straight chain right here, and those would be isomers of each other because they have the same molecular formula but a different structure. Here's another type of functional group. We can have different functional groups. Notice this has 2 carbons, 6 hydrogens, and 1 oxygen. Well, we've learned some functional groups earlier. We learned that an alcohol has an OH group and an ether has an ROR group, and these happen to be isomers of each other. Both of these, ethyl alcohol has a molecular formula of C2H6O, and dimethyl ether also has the same molecular formula, C2H6O. But they are not the same compound. The only thing they have in common is a molecular formula. They have different properties, they have different structures, different reactivities, all sorts of things are different between them. In fact, one of the most interesting features, I think, is the boiling points. Ethyl alcohol has a boiling point of around 78 degrees Celsius, whereas dimethyl ether, its boiling point is lower than room temperature, and actually dimethyl ether is a gas at room temperature. So that's pretty interesting. You have one that's a liquid at room temperature and the other one that is a gas at room temperature. We can also have different positioning, and this is also a constitutional isomer. Here we have C3H9N, and here we have nitrogen, NH2, coming off carbon number 2, and we have 3 carbons in a row, and my nitrogen's coming off carbon number 1. So these are also isomers of each other. So one of the things you need to do for this class is you need to be able to identify isomers of each other. You need to also figure out, given a molecular formula, how many different isomers you have. Conformation of alkanes. Now, these are not isomers at all. In fact, we need to pause for a minute on thinking about isomers. If you haven't learned isomers or practiced isomers, I think now's a good time to pause the video, go back and maybe work on isomers a little bit. This is something completely different, has nothing to do with isomers. Conformations of alkanes. I need you to build with your model kit butane again, 4 carbons in a row. We're going to make that model quite a bit. And I need you to put it in that zigzag pattern for the normal butane. So 4 carbons in a row, throw in all the hydrogens. Well, what I have on this page, take a look down at the bottom here, C4H10, I actually have different ways that we can show butane. Here we have a carbon here, and this intersection down here is the second carbon going down the chain. Going up the chain, a little further away from us, there's another carbon and his 2 hydrogens, and then going to the way, way back, there's another carbon. So you might want to go ahead and hold your molecule where you have a CH3 going off to the left. You have a carbon here, CH2, CH2, then a CH3. So what they're doing here is they're now going to keep the front carbon, the first 2 carbons, this carbon and this carbon, they're going to keep it still. Carbon 3 and 4 are going to rotate. So take your model and rotate it, and now make it look like this. Well, this conformer, and this is one conformer, and this is a second conformer, and we can rotate it again. This is a third conformer. All a conformer is, or different conformations, is taking the same molecule and bending and twisting it. It doesn't change the identity of the molecule at all. It just changes where they are relative just by spinning it. So these are all still butane. Rotation around a carbon-carbon single bond is an important property of alkane molecules. Alkanes have free rotation around a single bond. So you can take your butane molecule that you have and you can twist it between carbon 2 and 3 and you can make it look like a U shape. Or if you turn it upside down, it looks kind of like an N. But you can also take that same set of 4 carbons and rotate around carbon 2 and 3 and make it look like kind of a Z shape or the zigzag shape. That doesn't change it from being butane. It's still butane. It's just different conformers, different ways for us to rotate it. What we have up here is called the sawhorse representation. Now, beneath it, I have what's known as the Newman projection. And this one is where you take your model and you take a look at carbon 2 and 3 and you hold them eye level. And what's going to happen is you'll see on the first carbon, on the carbon number 2, the first carbon's going off this way. And behind it, you can't see carbon 3 because this one's in front of it. You can also see that the other carbon is coming this way. So this Newman projection matches this. Again, building the models in practice is the best way to do this. All right, we also have this projection. So all we're going to do is keep the front exactly the same and we're going to rotate the back 60 degrees. So this carbon here, I rotated between 2 and 3, so carbon 4 ends up coming up here, and that's what happened here. This is a Newman projection, and this one you can see that all these bond lines line up with each other. When all the bond lines line up with each other, that's called eclipsed. And when they don't line up with each other, that's called staggered. And we're going to see, you can almost tell by the Newman projection how this one right here, the eclipsed, is kind of stressed out. It's because too many atoms are close to each other versus this one where they're a little better spread out. And then we also, in this one, rotated it one more time. We took the back one, we rotated another 60 degrees, and you can go ahead and see what happens here. So definitely build your models. Oh, and I just noticed this 3 is not subscripted, so please fix that. I haven't noticed that before, so CH3 must be subscripted. Conformation of alkanes. As a result of the rotation around a single bond, alkane molecules, except methane, can exist in an infinite number of orientations or conformations. These, every one I have drawn in this box, are not isomers. They're the same molecule, C4H10. Every one of these in this box represent the same molecule, so they'd all have the exact same name. I want you to notice, and because we're going to be getting to naming in just a bit here, is when you go to name, you're going to look for the longest continuous chain regardless if it bends and twists. Notice this has 4 carbons in it and there's no branches coming off of it. So this name would be bute because it has 4 carbons and they're all single bonded, so it'd be butane. That's the name of this compound. Well, let's do the longest continuous chain regardless if it bends and twists. I have 4 in a row. There's no branches. It also has the name butane. And this one, still 4 carbons in a row, regardless if it bends and twists. This is butane, and in fact, that is actually the point. Regardless of the format that I draw this molecule, if I draw it zigzagged, I draw it over this way, or make it a U shape or an up down or an N, it's still butane. And here's a somewhat a zigzag shape going this way. Every one of these is still butane. Looking at it from different angles, free rotation around a single bond does not change the molecule. The molecule is the same. These are not isomers of each other, guys. One of the ways that I check if I have, when I draw out isomers to see if I've repeated or not, is I actually go back and name the molecules. I circle the longest continuous chain, regardless if it bends and twists. I number the branches coming off from the end that's nearer to give it the lowest number, and sometimes I'll come up with the exact same name and I'll find out, hey, this is not the isomer, this is not a new isomer, it's actually the same as something else, so I can cross that out.